We had just started talking about olfaction on Monday, and what we had gone through was the stimulus itself, those hydrophobic small volatile molecules, some of the functions of the olfactory system, and then we had just started talking about the basic detection, so detection thresholds. Is an odor present? And then we had gotten to this slide, which we got interrupted in the middle of why animals are so much more sensitive than humans. And of course, we can talk about the evolutionary sense that this makes, considering how much more they need their sense of smell because we have evolved our visual and auditory systems. But what I was getting at with the specific question was that they have so many more receptors than us, that one molecule of an odorant is going to cause one receptor to fire. And so the only way we can become more sensitive is to have more of those receptors. And I think we had gone through some of the species comparisons. I can't remember actually. So I'm going to start with the cats. I'm pretty sure I remember the first two have twice as many as people, mice having 2.7 times about as many as people. And I just really like this. Elephants can smell water about 19.2 kilometers away. So I don't think I smell water when it's sitting on my desk, and that is one of those things that's really impressive to me. Some basic examples of human odor detection thresholds come from, this is just a table from your book, and I'm going to start with the one that takes the least amount for us to smell it, is in this example is T-butyl mercaptan. That is a chemical that is added to natural gas so that we do smell natural gas, and all we need of that is 0.3 parts per billion in order for people to detect it. I'm going to just compare that to acetone, just for a nice, I think this is a good comparison because most of us have smelled something like nail polish remover. Acetone is often the solvent in nail polish remover, and that needs 15,000 parts per billion. So you can see how sensitive we are to the T-butyl mercaptan. My last bit about detecting odors and how we are getting these measures of thresholds. They've also taken difference thresholds. William Kane back in 1977, using cotton balls, found a difference threshold. So how much different do two odorants have to, do two measures of a particular odorant have to be for us to say yes, there's a difference. He found that difference threshold to be 19%. But he decided and concluded that there were differences in airflow and that there was lots of kind of what we might call situation noise in using cotton balls to do this. And so he came up with this olfactometer. So this, you can see where they are precisely controlling the amount of air and the amount of humidity and the amount of the odorant. And they are putting the other end of the olfactometer up into the person's nostril, and so we are taking out a lot of that situation noise. Using the olfactometer, that threshold dropped to just 11%. The next important aspect of the olfactory system to discuss is how we identify odors. So our recognition threshold, how much of an odorant that we need in order to recognize what the odorant is. We need a concentration of what we have for the detection threshold. We need that to be increased by as much as a factor of 3 in order to be able to recognize the odorant. Humans can detect as many as 1 trillion different odors. At least that is one estimate. Obviously, we've never tested people on 1 trillion different odors, but that is one estimate from one of the research studies. Recognizing those odorants is more difficult, and it appears to be that it's the memory for the odorant name that is the problem. And so one of the things I do after discussing the olfactory system, usually after, but sometimes a little bit during, is to have another class demonstration. And again, I'm going to really strongly encourage you to do this with someone else, to get a friend, a family member, whoever you're staying with right now, staying safe and socially distant from people, but get a friend or family member and have them choose maybe 3 or 4 different odorants, and you choose maybe 3 or 4 different odorants, so you can go around your kitchen. I usually go around the kitchen, and I actually have, I think I have 8 that are part of a recognition, where I give you choices, kind of like a multiple choice of what is this odorant. And I'm just going to give one example of, I usually choose whatever kind of citrus I have in my refrigerator, and then I give the choices of like lemon, orange, lime, or mango, or some other or maybe grapefruit, maybe another citrusy thing. But so, and then have people say whether or not they recognize them based on more this recognition ability versus recall ability, where I have another 8 odorants that I chop up or use spices or whatever, and I have them these little tubes, and I suggest strongly, again, so if you're doing this with a friend, 3 or 4 is probably sufficient for looking at the question, at least thinking about the question a little bit. And I'm going to keep coming back to this, so just remember this in the next lecture. That so what I did was I have them in the little plastic tubes, so that it's, and I suggest strongly that people don't use their vision, because that's cheating. You really want to use your olfactory system only. So again, you might blindfold your friend, or just suggest they close their eyes so they're not using their vision when they're smelling these things. So I have 8 with this more recognition memory, and then 8 different odorants where I use recall memory. And what I find every semester is that sometimes people aren't so great with the recognition. People are usually worse with the recall, and that is coming up with the odor, the name of the odorant. What we're going to talk about as we get into the higher level processing of smell and the olfactory system is that first primary receiving area is the information does not go through the thalamus, and that primary receiving area is communicating to all of these memory and emotionally associated memory areas and emotional areas. And so it's going through a really different route, and it's not really, that information is not coming back sort of out to the areas of the cortex where we remember things like names of things. It's going into our memory systems and our emotionally associated memory systems in a really different manner and in a much more direct manner. But anyway, it appears to be the memory for an odor's name that is the problem with our ability to recognize odors. Oh, and there is one more, so sometimes I can't go back and change. There is one more piece to the olfactory system, and this just background, and it is the puzzle of olfactory quality. So what we see is really similar molecular structures can create really different perceptions of odor. He gives us this example to the left of in A, of musk versus no odor, and you can see that there's very little that's different in those molecular structures. Again, I'm not a chemistry person, so I'm not going to pull it all apart, but you can just see that they are very similar, and yet musk is a really different smell than having no odor. We also have really different molecular structures where we are perceiving and experiencing a really similar odor. So if you look over in B, to the left, we have these 2 different molecules that are extremely different from one another in their molecular structure, and yet they both smell kind of like pineapple, and so they have a similar odor. And I have a green question here. I do suggest, again, that you pause these for just a moment and think about, before you get the spoiler, I'm going to answer you because I'm the only one here, but how is this different than vision and hearing? I usually get some real questioning looks from students, and eventually someone usually gets to this, and I can't even think of a lot of the different answers that I've gotten for this. But if you look at what's happening with vision, we have the electromagnetic spectrum, and things that are close on the electromagnetic spectrum are similar in their in the perception of the color, right? So if we're up at about 650 nanometers, we're going to see red, and then as we move down to 600 maybe nanometers, where it's going to start to look orange, and as we get down to actually 550 or so gets to green, so maybe 590, 580, we're getting to yellow. These are all approximates in my mind, so I'm looking at this in my head. But so, and then we move down to green. So as we are close to each other in what's out in the environment, the physics, we are close to each other in perception. And same with hearing, right? If we're looking at the frequencies and the different pitches, as those frequencies are 1200, 1250, 1300 hertz, we're going to be hearing a really similar kind of pitch. If they're really different from that and they're down at 200, 220 hertz, we're going to be hearing a really different pitch than the 1200, 1250, 1300. And the 200, 220, 230, those are going to be similar in pitch. So again, what's similar out in the world, the physics, the physical stimulus, we have a similarity in our perception. And this is different, clearly, right? As we're having really similar molecular structures, they don't smell anything alike. Really different molecular structures have a similar odor sometimes. This is sometimes, but very different than our other sensory systems. So I usually start out with moving to the next slide where there's a picture and then coming back and making sure I said what I wanted to say. And I have this horrible tendency when I'm looking at these slides to see what's on the slide and get very distracted actually by the words, as I'm usually not looking at the words anymore as I'm talking to my class. But here we are. And some of this is going to be repeated because I usually do this with the picture, and I'm going to continue to say what I want to say with the picture. But our olfactory mucosa are located in the upper region of the nasal cavity. They are made up of the olfactory epithelium, if that sounds like pigment epithelium. That is the back of the retina in the eye. The olfactory epithelium is basically like the retina of the nose, and that includes the retina of the nose includes the underlying tissue, the blood vessels, the glands, and the bundles of axon fibers from the olfactory receptor neurons. Okay, and it protects the olfactory mucosa protects the olfactory epithelium and allows odors to dissolve. So it's kind of moist up there, and it allows the odors to dissolve so that they can be detected by the olfactory receptor neurons. The olfactory receptor neurons are a lot like the rods and cones of the retina, and they are similar to the rods and cones in a number of ways. First, they contain those molecules that are sensitive to odorants, and this is similar to how the rods and cones have the visual pigment molecules that are sensitive to electromagnetic stimulation. They are made up of proteins that cross the membrane of the receptor neuron 7 times. And like rods and cones, they are sensitive to a range of specific stimuli. We're going to get back to that idea of the puzzle of olfactory quality, because while we have rods and 3 types of cones, and they are each responding, these 4 types of sensory receptors are responding to some range of the electromagnetic radiation that is close to us in the same area of electromagnetic radiation. We have 350 different types of olfactory receptor neurons, and for us to tell what a smell is, we're going to look at the pattern across 350 types of these different kinds of receptors. And just for comparison, there are 1,000 different types in mice, so they can detect, if we can detect, according to this one piece of research, supposedly about 1 trillion different odors, they can detect that many more because they have that many more different types of receptors, just like we saw with the animals that have 4 or 5 or 6 different cones, or I can't remember how many these particular kinds of shrimp have, something like 100 different cones. They're going to see a lot more variation in colors. These mice are going to smell a lot more variations in odorants. And I do have my word art up there to say this is where transduction is taking place, right, in these molecules that are sensitive to odorants. So transduction, I'm singing it so that we remember it's this wonderful magical thing that allows us to experience the environmental world. So with some repetition, here's my picture, and it's easier to talk in some ways from the picture that you can see. This is showing the olfactory epithelium, the olfactory mucosa down there, trying to show that it's moist in there, which allows the odorants to dissolve and hit those olfactory receptor neurons. And you can see the receptors kind of magnified there, that if a chemical is going to fit into that, that is going to affect that neuron, and we're going to see transduction. A few things he's showing here. So you can see the olfactory receptor neurons. He's showing them in these orange, green, and purple colors. He's trying to tell you about those 3 different types. Okay, so 3 different types of olfactory receptor neurons. Keeping in mind that we actually have about 350 to 400, so this is keeping it really simple. But one thing it allows him to show is, so these communicate up through the olfactory nerve and to the olfactory bulb. And they each type is going to communicate to a particular pair of glomeruli. So if you see that word up there, glomerulus is one a singular glomerulus on the olfactory bulb, and to a pair of these, glomeruli being the plural, we'll have a particular type of olfactory receptor neuron communicating to them. And again, responding to certain chemicals and not to other chemicals, while other olfactory receptor neurons are going to respond to other chemicals. So we're now looking at recognition profiles of various odorants, and what this is showing us is the particular olfactory receptor neurons that are active and just how active they are. So a large circle is that they are highly active, and the small circle there is that it is slightly active. And if you'll notice over to the right, our molecules, they look relatively similar, but remember the puzzle of olfactory quality is that even though we have similar molecules, they might have really different perceptions. We might have molecules that are very different from each other, and might have a similar perception. And what that perception, what that experience of the smell depends on is this recognition profile. And so he compares octanoic acid to octanol. Octanol is often described as a rose, kind of fresh, sweet smell, and octanoic acid is described often as rancid, or oh, I always forget what he calls it, sour, repulsive. And if we look at the recognition profiles for octanoic acid, we have olfactory receptor neurons 1, 18, 19, 41, 46, 51, and 83 are highly active, and then 79 also has some little bit of activity. And octanol looks really different, so 18, 19, 41, and 51. And this is just an example with a few of the olfactory receptor neurons, but you'd see that these would cause a different pattern of activation at the level of the olfactory receptor neurons. So just as a fun comparative, I got this information from Dr. Neil Levins. The bloodhound has about 220 million olfactory receptor neurons and 5% of cortex devoted to olfaction, compared to humans who have about 20 million olfactory receptor neurons and about 0.1% of the cortex devoted to olfaction. If you remember, so we talked about this for particular sense in the sense of a particular sensory modality, but if I have cortical magnification of something like my fingers, it gives me more acuity, more ability to feel detail. And I see the same thing with my vision, right? As we have cortical magnification of the fovea, and that's where I have the most detailed vision. So if we notice that they have 5% of their cortex compared to 0.1% for us, they have a lot more acuity or ability to smell. And while we can detect about the same number of smells as dogs, they can detect concentrations about 100 million times lower. And all of these, you might notice that my estimate here of humans before my estimate before of humans was about 10 million olfactory receptor neurons, and I think we said something like a billion for olfactory receptor neurons for dogs. If that's not in the previous slide, it's in the book. And just to notice that these are estimates from different people doing research. If we go back to our picture, I've already said some of this, as the axons of those olfactory receptor neurons are going to pass through that bony structure called the cribriform plate and bundle to form the olfactory nerve. You're going through that cribriform plate and that olfactory nerve is, and then it's entering the olfactory bulb. And again, much of this is repeating from the previous picture, but here I have another picture that shows nicely kind of what's happening with the glomeruli on the olfactory bulb, where we see this convergence of about 20 million olfactory receptor neurons are going to converge onto 6,000 glomeruli. And we've talked about what convergence gives us before when we talked about the rods and how they communicate. And as I mentioned before, with the green and the purple and the orange, but now he gives us blue and red, those olfactory receptor neurons that are expressing a specific type, olfactory receptor neuron type, they're going to converge onto one glomerulus pair. Okay, so a pair of glomeruli. So if we look at just as an example, if we look at the olfactory receptor neurons that respond to methyl salicylate, those are going to send axons to a single glomerulus pair. So we've been talking about what's happening at the level of the olfactory receptor neurons, and that we have this recognition profile and certain types of neurons responding to certain chemicals, and that what's really going to be changing in that recognition profile is going to, those different recognition profiles, if they're very different, it's going to mean different perception. And what we're seeing at the olfactory bulb, it's going to show activation of different areas for different chemicals, and that as we have the molecules, the chemicals, the chain length increasing, we see that area on this picture as moving farther to the left. And so if you see from the dark red at the very top that's a very short chain length, and as we move down to the blues, getting a longer and longer chain length, that's that activation as measured by oxygen consumption. So where there's less oxygen, we see that moving to the left on the olfactory bulb. But remember that part of what's important is the perception. And so what's happening, what we're going to see is the pattern of activation on the olfactory bulb. It's going to reflect the different chemicals and the chain lengths as we just saw, but it's also going to reflect different perceptions. And so I'm going to start with the ones that are the same. So if we move over to the right, the plus or minus limonene, those are very similar in perception. They're very similar in their chemicals and chain length, and we see very similar patterns of activation. If we look at the plus or minus carvone, those are very similar in their chemicals and their chain length, but now, or what the molecules look like and the chemicals look like in the chain length, but now we have different perceptions, and we can see this as there is a great deal of similarity across the olfactory bulb, but we see specific differences as well. And so what he's pointing to with the white arrows there is the one on the left in A. We have more activation up at the top and then over to the mid-right, and the one to the right in A is that has a different perception. We have less activation of what we just saw, of where those arrows were pointing, and now this white arrow is pointing of where we have a lot of activation in this example that we did not have in the one on the left. And so we're seeing similarity because of the chemicals and the chain length, but there are differences because we also need to code for the difference in perception. And so at the olfactory bulb, we're going to call this a chemotopic map, an odor map, sometimes called an odotopic map. But I think I'm pretty good at just sticking to chemotopic map, as it's a map. It's a chemically based map in this case. If you remember, we've had our primary receiving areas having something like a retinotopic map or a tonotopic map. And for sometimes we saw that as going through those subcortical structures. Here we are in the olfactory bulb, the very first place where olfaction synapses after being experienced by the sensory receptors. Okay, and as we look at what's happening here, the olfactory mucosa, so where the olfactory receptor neurons, those sensory neurons are communicating to the olfactory bulb, and the olfactory bulb is communicating directly to the piriform cortex, which is the primary receiving area for olfaction. So the primary olfactory cortex is called the piriform cortex. But look, it's not just communicating directly with the piriform cortex, so i.e. not going through the thalamus like we have seen for every other sensory modality so far. It's also communicating directly with the amygdala. And actually, so usually we read a journal article here about the sense of smell and about the piriform cortex and its mapping, that it is communicating across the entire hemisphere to all of those limbic system regions, the entorhinal cortex, the hippocampus, the amygdala, and the orbitofrontal cortex. And it has these neurons that, instead of communicating to other neurons close by that are doing something similar, they are communicating across the hemisphere to thousands of neurons. And the neuron next to me, if I'm a particular neuron, is not going to necessarily be communicating to the same neurons that I'm communicating to, or even neurons that are close to what the neurons that I'm communicating to. In fact, they looked at two neurons close to each other in the piriform cortex, and they had almost no overlap in the neurons that they were communicating to. And again, thousands of neurons across the hemisphere. And so what's happening, as we're going to talk about this experience of olfaction, and I've already commented on how we don't remember the names of what we're smelling very well until somebody tells us the name, and then the quality actually can change based on that experience. But what we often remember with the sense of smell is memories, and especially emotionally associated memories. And it has this vivid sense where we tend to feel some sense of emotion when we are smelling something, and that is because of this. It's not going through the thalamus. It's not going to these higher level visual areas that are then, or visual or other sensory areas that are doing the same kind of information processing. It is going throughout the hemisphere directly from the olfactory bulb, which comes directly from the olfactory receptors themselves.